Hello, welcome to this lesson on half-lives. The question of the day, how do unstable nuclei work to become stable? Because chemistry is all about reaching stability. All right, we already know from the nuclear reactions lesson and the types of radiation lesson that anytime you have a radioisotope, it is going to the nucleus rather, is going to slowly break down over time in order to become more stable. In doing that, it's going to emit energy, and sometimes it also emits particles. Now, the rate of decay is called half-life. Well, that's really how we measure it. And sometimes this radioactive decay is going to form new elements because you're emitting particles from the nucleus. So in doing that, you can change the number of particles in the nucleus, thus giving you a new element. So the half-life is the amount of time it takes for half of a sample to decay. I kind of have it here where half of the sample would be radioactive and half of it would be decayed in the first half-life, rather. What happens is that the goal is something that is more stable. Just because something is decayed doesn't mean that it's not radioactive. It's just a new type of radioactive. So you may have a uranium that degrades into a thorium, but the thorium may still be radioactive. So this is not to say that when something decays or degrades, that it immediately becomes stable. It's just on the path to stability. So the first half-life, half of your sample would still be that original radioactive substance. Let's say it's the uranium-238. And then the other half is going to be decayed, broken down a little bit smaller. And then in this case, this might be thorium. And the thorium may still be radioactive, but it is the decayed version of uranium-238. I hope that's making sense. Now, in the second half-life, your original sample, which was the 50%, is going to get cut in half again. So now only a quarter of your original sample is going to remain in its original sense. And the decayed region of this pie chart is going to be much larger. Now, if this sample itself is radioactive, then that would be broken into a new pie chart. That would be its own 100% that then has to degrade half by half by half. We're not focused on that right now, but just so you know that is a possibility. So over time, of course, this radioactive chunk is going to shrink and shrink and shrink and shrink. And then the decayed region of the pie chart is just going to grow bigger and bigger and bigger. Some radioisotopes are going to degrade or decay faster than others. And there's not really a pattern to it, at least that I can tell. Some things have tens of thousands of years for their half-life, and other things are milliseconds. They degrade very quickly. Now, typically the things that degrade quickly emit a lot of radiation all at once, so they're not super safe. The things that have a longer half-life are radioactive for a longer amount of time, so a different kind of dangerous, if you will. Again, some things are just more dangerous than others. It also depends on the penetrating power of this type of radiation, whether it's alpha, beta, or gamma. And then also the amount of stuff that you have. A pound of uranium is going to be far more dangerous than a gram of uranium, right? So those are all things to consider when we're talking about the danger of these isotopes. And in case you're interested, there are a lot of scientists trying to figure out how to make this process faster and easier and safer. And this is more so related to nuclear power. If, let's say, we're using uranium-238 to run a power plant, and it is going to break down into thorium for its, when it breaks down, when it degrades, the idea is that you would want to then take that thorium, which is radioactive, and put it in a new nuclear reactor and react that again. And that would be like recycled nuclear waste. You get to use the product of this a second time, which would be really cool. Because then you don't have to harvest as much uranium in order to run this power plant. And then that thorium will break down into something else, which might be able to be recycled. And then again, you may be able to use that over and over again until you come down to something that's really stable. And that would probably be done by a fission reaction where you take a neutron and kind of blast it at this uranium or thorium sample and break it apart in those chain reactions. I'll link the nuclear reactions video in the description of this one so you can get a good look at that. So how does this apply to us? When we're watching not watching, but when we're looking at a radioactive isotope breaking down, we can determine what fraction, what percent, or what mass of this sample will be left after a certain amount of time has passed. This is also good if you are interested in the medical field and looking at like diagnostic medicine. Like I had mentioned in the uses of radioactive isotopes, using tracers, you want to know how long this thing is going to be radioactive in somebody's body before either their body gets rid of it or the thing decays on its own. So we can look at kind of a chart to show us how much is going to be left after a certain amount of time. I've seen a lot of people teach how to do half-lives, but I really think this is the easiest way to do it. So what we're going to do is take the value that's in the question, the given amount, and we are going to run that across the top of the table. So in the case of asking about fractions, we would put a fraction on the top. You have 100% to begin with, so that fraction would be 1 over 1. After one half-life, you would have half of that sample left, so now your fraction would be 1/2. Then, just like that pie chart, when we break it down again, it would only have a quarter. And then after that, the quarter splits in half and we have an eighth. So if we're running with fractions, that's the thing that we're looking for, then we would run fractions across the top of this graph. But we could also do that with percents or even with mass in grams or milligrams. And that would run across the top. Then across the bottom, you would have the half-lives. Now, the half-life is the amount of time that you need for this sample to decay 1/2 of its mass. At the very beginning, you are at time equals 0. That is when you begin, and then you would add the half-life going on. So if, for instance, the half-life of carbon-14 is roughly 5,700 years, in the first section here, you'd have 5,700, and then this would be another 5,700, which would bring you to 11 something, 12, 11 something. I don't know. I can't do math. And then you would add it again and again. So it's always, you begin at time equals 0, and you'll see it as it kind of plays out here. So again, that top row, which is either going to be fraction, percent, or mass, is going to be cut in half with each successive half-life, because the half-life is the amount of time you need for half of the sample to decay or to degrade. So up top, your fraction, you start out with 1 over 1, then it becomes 1 over 2, then 1 over 4, then 1 over 8. When you're dividing fractions, you just double the denominator. Then across the bottom, you would add the half-life with each successive section of this table. But if you don't have this specific half-life, like carbon-14 is 5,700 years, if you don't have that, then you can just count half-lives. Of course, remember, timer starts at 0, and then every half-life would be 1, 2, 3, 4, 5, or it would be that 5,700 plus 5,700 plus 5,700 going through the whole table. Okay, so here's our first example. It asks what percent of carbon-14, oh, that's spelt wrong, remains, I will fix that, after 5 half-lives. So we are first working with 100% of our sample, and we are at half-life 0. Time is starting right now. So the first thing that we're going to do is cut our sample in half. So now we're only going to have 50% of the sample, and 1 half-life has passed. After that, we will have, in the second half-life, only 25% of the sample remaining. We'll keep it moving. In the third half-life, we'll only have 12.5%, of course, cutting it in half. And the fourth half-life will yield 6.25% of the original carbon-14 sample. Finally, in the fifth half-life, we will only have 3.125% of the original sample remaining. And I don't think we need to worry about significant figures for this particular problem, so that would only leave us with a final answer of 3.125% of the original sample remains. Okay, here is another example, still using carbon-14. We are starting with a 1.20 gram sample of carbon-14, and it has been left to decay. And the question is, what mass would remain of the original sample after 22,920 years? Okay, so up top, we're going to put the mass. You should put a unit here, grams. And again, we're counting years, but time is equal to 0. We're starting the timer right now. Now, the half-life of carbon-14 is 5,730 years. So up top, we are going to cut the mass in half. So now we're down to 0.60, and only one half-life has passed. So we are at 5,730 years when we only have 0.6 grams of the sample. Now, after another half-life on the bottom, we're adding that 5,730. That brings us to 11,460 years. And the original sample would have to be cut in half for the second time, giving us 0.3 as the mass. Now, in the third half-life, 17,190 years have passed, and we take that 0.30 and divide it by 2. We're chopping it in half again, and now we are up to 0.15 grams. One more half-life will bring us to the amount of time that the question asks about, which is 22,920 years. And we, at that point, would be left with 0.075 grams of the original sample. I really find that using this table method is the easiest way to do it. It keeps you very organized, and I just love it. I think it's the best way. I've done this a few times, and I've taught a lot of students. I think this is the easiest way to do it. So that's everything. If you have any questions, of course, please feel free to leave them in the comment section below the video. Subscribe so you don't miss the next lesson, and I'll see you there. Bye.